You're listening to DTFHN for May 30th, 2026. I'm your architecturally load-bearing host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where strangers argue about where to draw the line and then draw it wrong. Today's a day for boundaries, the ones we build and the ones that outlive us. Let's get into it. I've spent enough time staring at build system architectures to know that the boundary between configuration and execution is where most of the complexity hides. You draw that line wrong, and every developer pays for it on every single build. Andrew Kelly just redrew that line in Zig, and the results are remarkable. Here's what landed. Zig's build system used to compile everything. Your build.zig logic plus the entire build run into one process in debug mode. Every time you ran Zig build, you paid the full cost. The rework splits this into two processes, a configurer and a maker. The configurer compiles just your build.zig logic. In debug mode, constructs the build graph and serializes it to a binary configuration file. The maker, compiled once per Zig version in release mode and cached globally, reads that file and executes the graph. The benchmarks tell the story. Running Zig build help went from 150 milliseconds to 14. That's a 90% reduction in wall time. CPU cycles drop 95%. Instructions drop 95%. Cache misses drop 78%. These aren't marginal gains from micro-optimization. This is what happens when you rethink the architecture. The elegance here is in the layering. Your build logic only recompiles when it actually changes. The execution engine compiles once and benefits from release mode optimizations forever. And the system can now skip rerunning your build.zig entirely when it knows the configuration hasn't changed. Like when you're just adding a flag. That last part is subtle but powerful. It means the build system understands the difference between what you're configuring and how you're running it. There's a secondary benefit that might matter even more long-term. That serialized configuration file becomes a stable interface. Tools like ZLS, Business Language Server, can consume it directly instead of maintaining a fork of the build runner. One clean boundary, multiple consumers. This is how you build an ecosystem that compounds. And all of this is open. The PR is linked. The internals are documented. The devlog reads like engineering notes from someone who respects your time enough to explain the trade-offs. One commenter called Zig a fantastic tool language. Something you just pick up to hack ideas together freely. Another called it the language for artisanal Japanese carpenters. I love that framing. Precision tools, no wasted motion. Every joint load-bearing. What Kelly and the Zig team keep demonstrating is that performance isn't about heroic optimization. It's about finding the right separation of concerns and then executing cleanly on both sides of the boundary. The configurer does configuration. The maker does making. Each compiled appropriately for its job. The tools exist. The source is available. And if you want to help test it, the branch just landed on main. Moving on. In 1980, a group of IBM managers in Boca Raton made a decision that restructured the entire computing industry. They chose to build the PC from off-the-shelf components, and crucially, let Microsoft retain the license to DOS. This wasn't visionary. It was the path of least resistance chosen by middle managers under deadline pressure. Following standard procurement logic, nobody in that room understood they were handing the next 30 years of computing to a kid from Seattle. The most consequential architectural decision in personal computing history was made by people who were, by every available account, simply doing their jobs adequately. This is the premise worth taking seriously from a recent essay on what the author calls a mediocre man theory of history. The argument, grounded in the case of Kaiser Wilhelm II, is straightforward once you strip it to first principles. There are three actual variables in how history unfolds: structural forces, economics, demographics, technology, individual agency, the decisions specific people make, and the third variable, the one most often ignored, competence, or more precisely, the lack of it. Wilhelm wasn't a tyrant in the classical mold. He wasn't a strategic genius. Recent scholarship from John Rule and Annika Mumbauer establishes that he did centralize real power after his accession. This wasn't a figurehead, but the power he accumulated was wielded with the judgment of someone you wouldn't trust with the departmental budget. The counterfactual is devastating in its clarity. Replace Wilhelm with someone possessing his grandfather's temperament or his father's liberal instincts, and the 20th century becomes unrecognizable. The first principles here matter. We tend to model leadership failure as either systemic, the structures made it inevitable, or exceptional, the work of uniquely terrible individuals, but most catastrophic decisions live in neither category. They're made by ordinary people operating at the ceiling of their abilities in roles that demand far more. The structural forces create the conditions. The individual creates the specific disaster. This maps onto every system where power concentrates without corresponding accountability. The question is never just who holds authority, it's whether the architecture around them can absorb their limitations. Open systems distribute that risk. Closed systems, monarchies and monopolies alike, concentrated in whoever happens to be sitting in the chair. Wilhelm's Germany had no error correction. The feedback loop between bad judgment and catastrophic outcome was a straight line. That's the architectural lesson worth carrying forward. Not that mediocre people reach power, because that's inevitable, but that closed systems let mediocrity compound unchecked until the whole structure fails. Moving on. Document formatting is, at its core, a separation of concerns problem. You have content, the actual words, the research, the arguments, and you have presentation. Margins, fonts, heading styles, page numbering. The history of word processing is largely a history of tangling these two layers together and then struggling to pull them apart. In 1974, Brian Kernighan and Joe Osana's TOF system on Unix got this right from the start. Plain text in, formatted output out. The content lived in one layer, the formatting instructions in another. You could swap the presentation without touching the substance. Then the WYSIWYG revolution of the 1980s collapsed both layers into a single opaque binary format, and we've been paying for that architectural decision ever since. Clément Aubert, a faculty member at Augusta University School of Computer and Cyber Sciences, has built a Pandoc-based thesis template for master's and PhD students. The functional details are straightforward. Students write in Markdown or LaTeX. Pandoc handles the transformation to whatever output format the graduate school requires, and the template encodes all the institutional formatting rules. Margins, title page layout, chirography style. So the student never manually adjusts them. What makes this worth examining is where it sits in the academic tooling landscape. Most universities hand graduate students a Word document template. The student writes their entire dissertation inside that template, and every formatting rule is embedded in the document itself. Move a figure, and the page numbers break. Change a heading, and the table of contents desyncs. The content and the presentation are fused at the file level, which means every edit to one risks corrupting the other. The Pandoc approach restores the original Unix architecture. Content stays in plain text files that any tool can read, any version control system can track, any search utility can index. The formatting rules live in a separate template that can be updated independently. Aubert even notes that students uncomfortable with this approach should use the standard Word template instead. A practical concession that quietly underscores the point. The institutional default is the less capable tool. A single thesis template at a single university is a small thing, but the pattern it represents. Plain text in, structured output out, content and presentation cleanly separated, is the same pattern that scales from one graduate student's dissertation to entire publishing pipelines. The tools exist. They've existed since 1974. Every time someone builds another template like this, they're making the on-ramp a little more walkable for the next person who needs it. Moving on. Let me make the strongest case against this idea first. SQLite has no concurrency model worth mentioning for multi-writer scenarios. It's an embedded database. The whole point is single process access. One commenter on Hacker News put it bluntly. SQLite is completely unsuitable for managing concurrency, and that's what database servers are for. If you're building production infrastructure, why would you reach for a tool that can't handle two processes writing at the same time? Fair point, and it's exactly the wrong frame for what's actually happening here. The article from the Obelisk project isn't arguing that SQLite replaces Postgres in your production stack. It's arguing something more specific and more interesting. That durable workflow execution. The part where you track what an agent did, what step it's on, what needs retrying, doesn't need a shared database at all. The durable part is the state. The compute is disposable. And if each agent or tenant gets its own tiny database file, you've just eliminated the concurrency problem entirely. There's one writer. It's the agent problem solved. This is the architecture insight that the just use Postgres crowd keeps skating past. When you give every workflow its own SQLite file, you get transactional durability with zero network hops, zero connection pooling, zero operational surface area. Pair it with lead streaming changes to S3, and you've got backup and portability without running a single additional service. The trade-off is real. Async replication means you could lose the newest writes if the volume vanishes. But for explainable AI workflows, that's an acceptable bet. One commenter listed everything they'd replaced with Go plus SQLite, Intercom, Zendesk, email marketing, billing, issue tracking, uptime monitoring. That's not a theoretical argument. That's someone who shipped it. The comedy here, and I say this with genuine appreciation, is that the database world spent 2 decades building increasingly elaborate distributed systems to handle scale, and the emerging answer for a huge class of AI workloads is a single file. Richard Hipp's 40-megabyte library, running in a container that might live for 6 minutes. The Obelisk project is open source, written in Rust, and the architecture is exactly the kind of thing this show exists to celebrate. Small, composable, inspectable. Each database file is a complete record of what an agent actually did. You can replay it, debug it, hand it to someone else. Try doing that with your temporal cluster. Postgres is there when you need it, but the default should be the simplest thing that works. For a fleet of AI agents doing bursty experimental work, that's a file. Earlier, we talked about who controls the infrastructure. Turns out that question applies to rockets too. And one Danish pension fund just drew a line. What does it mean when the people whose job is literally to think in 50-year time horizons look at a company and say, no, the governance isn't there? Akademiker Pension, a Danish pension fund managing retirement money for academics and professionals, just excluded SpaceX from its portfolio. The reasons they gave are worth sitting with: governance concerns and valuation. They'd already excluded Tesla on similar grounds. And here's the detail that makes the conventional objection fall apart. This fund has been one of the top performers among Danish pension funds over the past decade. Plus, this isn't idealism sacrificing returns. It's discipline producing them. The valuation question is the one nobody in Silicon Valley wants to engage honestly. SpaceX is reportedly valued at $1.8 trillion. Trillion. For a company whose primary revenue stream is launching things into orbit and selling satellite internet. Starlink is genuinely impressive engineering. A mesh of thousands of satellites providing broadband to places fiber will never reach. The rockets land themselves. The engineering craft deserves every bit of admiration it gets. But $1.8 trillion is not a valuation of engineering. It's a valuation of narrative, of proximity to a single individual's brand. And when a pension fund, whose fiduciary duty is measured in decades, looks at that number and walks away, that's not timidity. That's math. The governance piece cuts deeper. When a company's decision-making is opaque, when there's no meaningful board independence, when the entire strategic direction can pivot on one person's attention. That's not a bet, it's a dependency. The commenters on this story raise something I keep turning over. The growing tension between passive index investing and companies that trade at massive capitalizations with negative earnings. If your index fund is market cap weighted, you're automatically buying more of whatever is most expensive. You're not making a choice. The choice is being made for you by momentum. What Academic Pension did is actually choose. They looked at the structure, not just the stock price, and asked whether the architecture of this company, who controls it, how decisions get made, what happens when incentives shift, justified the risk. That's the kind of question that applies far beyond finance. Every system we build, every platform we depend on, has a governance architecture. The ones that endure are the ones where you can see the wiring. We talked about seeing the wiring pave well. Some folks just reverse engineered all the wiring. Story 6. Snowboard Kids 2 is 100% decompiled. There's a line buried near the bottom of Chris Lewis's blog post that deserves more attention than it gets. Quote, a 100% match doesn't mean the source is perfectly understood. He's talking about Snowboard Kids 2, the 1999 NID 64 racing game, which he just finished decompiling entirely into C. Every function now compiles back to assembly that is byte identical to the original cartridge ROM. And yet, he says, many functions still have generated names. Structures need cleanup. Graphics and audio assets are binary blobs. This is the paradox of translation from a dead language. You can produce a text that, when fed back through the original grammar, regenerates the source manuscript perfectly, and still not know what half the words mean. The Rosetta Stone didn't decode Egyptian because someone matched the glyphs. It decoded Egyptian because someone understood the relationships between them. Lewis has built the Rosetta Stone. The full translation is next. The project took just under 2 years. The final functions were matched while Lewis sat in a hospital room with his newborn daughter, who needed help eating. Decompilation, he writes, was a useful distraction during the quiet hours. There's something fitting about that. A person reconstructing the internal logic of a 27-year-old game while watching a brand new human figure out the internal logic of swallowing. The work was not solo. The N64 decompilation Discord community contributed directly, with 4 members credited on the hardest final 10 functions. Lewis also used coding agents, Claude and Codex and GLM, and offers a pragmatic observation. Frontier models are now very effective at decompilation, but which model leads keeps changing. GLM, he notes, has been the best value. If subscription fees are stopping you, start there. What matters here is the output. The entire code base is public. Anyone can read it, build it, study it, mod it. Lewis's next goal is a recompiled version, already showing widescreen and extended draw distance. After that, he wants to decompile the first Snowboard kids and potentially merge both games into a single engine. This is what preservation actually looks like, not a ROM dump sitting on an archive.org page, not emulation that approximates, a living codebase that compiles, that you can fork, that turns a locked cartridge into source code anyone can touch. The game's original developers wrote this code in C, compiled it, shipped it on plastic, and moved on. 27 years later, a person in a hospital room, helped by a community and a handful of language models, pulled the C back out of the silicon. The ROM is the artifact. The decompilation is the knowledge. One sits on a shelf. The other multiplies. 7 stories in, and we haven't even hit the pure computer science yet. Let's fix that. Resumable exceptions. That's the core idea buried under years of intimidating academic PDFs. And it's so elegant, it's almost annoying that we don't have it yet. Dan Abramov wrote this explainer back in 2019, and it holds up beautifully because the concept itself is timeless. You know, try catch. You throw an error, it bubbles up the call stack, some handler catches it, and you're done. The original code is gone. You can't go back. Algebraic effects ask a simple question. What if you could? Imagine throwing an exception, having a handler somewhere up the stack provide a value, and then resuming execution right where you left off. The throw becomes a request. The catch becomes a response. And the code in between never has to know it happened. That separation. The code that needs something from the code that provides it is the entire game. Follow this to its logical extreme and watch what happens. Dependency injection. You don't need a framework. Your function performs an effect. A handler provides the implementation. Done. Testing. Wrap your code in a handler that provides mock values. The function under test never imports the mock, never receives it as a parameter, never knows. Async operations? Same mechanism. Perform an effect. Let the handler decide whether to resolve it synchronously or asynchronously. Resume when ready. React suspense already works this way conceptually. A component throws a promise. React catches it, waits, then re-renders. That's a resumable exception with extra steps. The Hacker News comments nail something important. One commenter points out these are essentially dynamically scoped callbacks. Functions declare what they need. Handlers anywhere up the stack provide it. And the middle layers stay clean. Another notes that OCaml 5 has a working production quality implementation now. This is programming language research, doing what it's supposed to do. Finding the primitive that unifies patterns we've been hand-rolling for decades. Dependency injection, async control flow, error recovery, mocking. All different costumes on the same idea. One construct. The academic papers made it sound alien. Abramov made it sound obvious. That's the crap. Not inventing the concept, but translating it so clearly that you wonder why every language doesn't already have this. Now, sometimes the primitive you need isn't hidden in a type system. BMake. It's buried in the silicon itself. -1.175 times 10 to the -38. That number sits in a strange no-man's land of Iobata E754 floating point representation, right below the threshold where normal encoding runs out of room and subnormal numbers take over. Adam Sawicki's latest deep dive asks a deceptively simple question. What happens when you call floor on it? The mathematically correct answer is -1. The number is between -1 and 0, so floor pushes it down. Every programmer who passed a numerics course knows this. But here's what actually happens on a GPU. Many graphics processors flush subnormal numbers to 0. Silently, no warning, no error, no flag. Your tiny negative number becomes 0, and floor of 0 is 0. Not -1, 0. The same input, the same function name, the same mathematical specification, and you get a result that's off by exactly 1. In graphics rendering, nobody notices. A color value shifts by an imperceptible amount, but the moment you use floor or Ceil for logic, for indexing, for any discrete decision, that silent flush turns into a hard bug that only manifests on specific hardware. This matters because it's a concrete example of something developers rarely think about. The silicon under your code is making editorial decisions about mathematics. CPU vendors chose to preserve subnormals. GPU vendors chose speed over precision and flushed them. Neither is wrong in isolation, but the divergence is invisible at the API level. You write floor, you expect floor, you get something else, and the specification technically allows it. Pull this thread further. GLSL leaves the rounding behavior of its round function implementation dependent. The shader language that runs on billions of devices doesn't guarantee which direction halfway values go. Every GPU vendor gets to decide independently. The developer gets to discover the inconsistency in production. The tools to understand this exist. Sawicki's floating point formats cheat sheet has been public since 2013. The IEEE 754 spec is well documented. The knowledge is available, but the hardware abstraction layers we depend on are actively hiding the divergence rather than surfacing it. When your platform silently changes the result of a math function based on the magnitude of the input, that's not an optimization. That's a leaky abstraction with real consequences. And the people writing shaders deserve to know exactly where the floor falls out from under them. Moving up. When you've spent enough time building distributed systems, you develop an instinct for a particular architecture pattern. The company that stops trying to win on any single layer and instead owns the entire stack. Mistral just made that move. The numbers are worth stating plainly. A 40-megawatt data center in Paris, more facilities planned in Sweden, their own compute, their own models, their own deployment platform, their own consulting arm. This is not a model lab anymore. This is vertical integration with a European passport. Run this forward. An Austrian research team fine-tuned Mistral's cadastral to decipher ancient papyri. 180,000 documents pulled from Egyptian desert sand, work that would have taken 2 millennia by hand. BNP Paribas runs Mistral on-prem for Know Your Customer compliance in Belgium. Sensitive financial data never leaving the bank's infrastructure. The EU Patent Office uses their document AI for optical character recognition at scale. These are not benchmarks. These are production deployments solving problems that existed before the hype cycle. The strategic bet is specialized small models over general-purpose giants. Voxtral handles multilingual voice for Amazon's Alexa Plus across Europe. Robostral drives industrial robotics alongside ASML. In each case, a focused model tuned for a specific domain outperforms the flagship behemoths on the metrics that actually matter in deployment. Latency, energy consumption, cost per inference. The comments from practitioners tell a consistent story. Mistral's reasoning capabilities have fallen behind the frontier lab since late 2025. Government evaluators want to use European models but find the gaps difficult to justify. This is the tension at the core of the whole project. But here is what the open model architecture makes possible that no amount of API access ever will. A Belgian bank running sovereign AI on its own hardware, a classics department in Vienna teaching a language model to read Greek cursive from 2,000 years ago. The models are open. The weights are downloadable. The fine-tuning is yours. That is infrastructure you can build on. Everything else is a rental agreement. Now shift gears entirely from the cutting edge of AI infrastructure to something beautifully analog, POSAX, saving data one floppy disk at a time. In 1984, the BBC Domesday Project tried to create a digital time capsule of British life. They stored it on custom laserdiscs using a proprietary format readable only by a modified Philips player. By the mid-90s, barely a decade later, almost none of the hardware still worked. Meanwhile, the original Domesday Book from 1066, Income Valum, remains perfectly legible after 960 years. The comedy writes itself, but the lesson is architectural, and Leontien Talboom's floppy disk preservation work at Cambridge gets at exactly why. The physical degradation is real. Iron oxide flaking off plastic substrates, mold colonizing disks left in attics for decades. But the harder problem is the knowledge layer. Talboom describes going to retro computing communities to learn tricks like flexing a 5 1/4-inch disk casing to unstick the magnetic donut from the shell. That's not documented anywhere official. That's tacit knowledge living in the heads of hobbyists. And those hobbyists are aging out. Here is where the open-closed architecture becomes load-bearing. The well-loved home computer. Your ZX Spectrums, your BBC Micros, your Amstrads. Those file systems are extensively documented because communities of enthusiasts kept the knowledge alive and shared it freely. The business and research systems, proprietary formats, proprietary file systems, documentation locked behind companies that no longer exist. Talboom says, those are the ones that are genuinely difficult to recover. The pattern repeats across every era of computing. Open documentation survives. Closed documentation dies with its vendor. One commenter mentions Grace Wesel, an open-source hardware tool that reads raw magnetic flux from any floppy disk, regardless of format, $20 in parts. Schematics published. That single open-source project has probably saved more archival data than any institutional preservation program. The tools exist because someone put the blueprints where others could reach them. Talboom's real insight is the last one. The best storage strategy is active stewardship. Transfer, monitor, migrate. Not write once and forget. Preservation is a verb, not a noun. The floppy disk didn't fail because the technology was bad. It failed because we treated storage as a solved problem and walked away for 30 years. This has been your daily tech feed for Hacker News for May 30th, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that outlasts the format it ships in. We'll see you back here tomorrow.